Okay, now, if F is a force field, then the integral of F dot ds along any given path is the work done by the field in moving along the path from one point to the other. Because your ds stands for the delta S along your path, and you know that the force dotted with delta S gives you the work. Okay, your force dotted with a displacement gives you the work. So that's a very simple and straightforward consequence of the way we define work. So the work due to the gravitational force is what? Well, we could do the line integral, and we're going to do we're going to do a couple of line integrals. We're going to at least write one down, then we're going to do another one that actually calculates the work between 2 points in a gravitational field. But we don't have to do that, and that's one thing we're going to verify, at least for the points that we, and paths that we use. The fact that F is a conservative field, that F is the gradient of little f, tells us that we can apply this criterion, or this characteristic, the integral of F dot ds, which is what we're doing between 2 points, is just going to be little f evaluated at the second point minus little f evaluated at the first. Okay? And since we know our little f function, it's going to be rather straightforward. As a matter of fact, another way of writing our little f function is big G little m1 little m2 over r square over r. Okay, and I probably should have. It was clear to everybody when we did it in class, but this is just then G little m1 little m2 over r. Because square root of x squared plus y squared plus z squared is your r, your distance from the origin out to the m2 point. That means that little f at x2, y2, z2 is just g m1, m2 over what? The r at that point, we'll call that r2. So you're going to have, and for the x1, y1, z1 point, we're going to call that square root for the x1, y1, z1. We're going to call that r1. So that you're going to have big G little m1 little m2 over r2 minus big G little m1 little m2 over r1. And factors out into this expression. Okay? And that being the work done by the field when you move from one point to another, if you are aware of the physics, that's your change in potential energy. That's equal and opposite to your change in potential energy. So your potential energy change depends only on your starting and ending distances between the two masses. And that's a very profound result, and we get that sort of thing with electrostatic fields, with magnetic fields, etc., etc. Very common result, and it saves us a lot of work to understand this.